Hello. In the following, we will present Neu-PiG, neural preconditioned grids for fast dynamic surface reconstruction on long sequences. The task we address is dynamic surface reconstruction from point clouds. Given a sequence of unstructured point clouds over time, we want to recover a coherent surface representation that follows the motion of the observed object. This becomes especially challenging for long sequences. Errors can accumulate over time, correspondences may drift, and many existing optimization-based methods become very slow as the sequence length increases. Existing methods often face a trade-off. Optimization-based approaches can produce high-quality results, but require long runtimes. Learning-based methods are faster, but usually rely on category-specific priors or training data. Our goal is a fast, prior-free method that reconstructs dynamic surfaces without requiring explicit correspondences. We start by selecting a representative keyframe from the input sequence, biased toward the temporal midpoint. From this point cloud, we reconstruct a reference mesh using screened Poisson reconstruction. This mesh defines our canonical space. Its vertex positions and normals are used as queries for all later deformations. The key idea of our method is to avoid optimizing independent deformations for every frame. Instead, we use one shared latent representation for the whole sequence. Each vertex of the reference mesh queries this latent space using its position and normal direction. We represent this latent space with a multi-resolution grid. This allows the model to capture coarse, global deformation patterns at low resolutions, while finer levels can represent local geometric details. The important part is that the latent grid is optimized with Sobolev preconditioning. This smooths the gradient updates over neighboring grid cells, which encourages spatially coherent latent features and helps avoid drift over time. To make the static latent space time-dependent, we add a Fourier time encoding. Each time step is normalized and mapped to sinusoidal features. These time features are concatenated with the position and normal latent features, allowing the decoder to represent both slow and high-frequency motion. The decoder we use is a lightweight MLP. For each reference vertex and time step, it receives the latent features and the time encoding and predicts a time step-specific motion. In particular, it outputs a rotation and displacement for each vertex. The latent grid itself is shared across all time steps, but the decoder becomes dynamic through the time encoding. Applying the predicted rotation and displacement to the canonical reference mesh gives the reconstructed mesh at a specific time step. We evaluate on standard dynamic reconstruction benchmarks, including human and animal sequences. Across these datasets, Neu-PiG achieves the best reconstruction accuracy and temporal consistency while reducing runtime from minutes to seconds. Qualitatively, we see that our method preserves the shape more accurately and avoids strong artifacts. In the error visualization, our reconstruction is closer to the ground truth while also being much faster than prior optimization-based approaches. We also evaluate scalability on longer AMA sequences. This is where accumulated drift becomes especially problematic for previous methods. We remain stable, while the other methods degrade strongly and become extremely slow. For example, on a 40-frame sequence, we are able to reconstruct the sequence in under a minute, while prior optimization-based methods take tens of minutes. On longer sequences, the runtime gap becomes even larger, while our method still maintains coherent reconstructions. To summarize, Neu-PiG enables fast, prior-free dynamic surface reconstruction from point cloud sequences. By combining a canonical reference mesh, preconditioned latent grids, and a time-conditioned decoder, we obtain high-quality and temporally stable reconstructions in seconds. Thank you for watching, and feel free to reach out if you have any questions or would like to discuss the work further.